Hello. Welcome into the journey to the quantum world. Imagine tonight your best friend is calling you to come to a really nice party. Cool, right? You're gonna have fun, dance, play, whatever you want. It's a great party. Okay. At the same time, your parents say, hey, baby, let's go to see this great movie tonight. Cinema is showing your favorite one. Let's go to see it together. It's like, it's not often your parents often that, but kind of cool. Right, party tonight, cool movie tonight, great things. But you are one. To be able to go, you need to be in two places at the same time. I tried many times. All 34 years I am trying that. It does not work. Right. I'm Oxana. I'm a physicist, and I come from Russia, but now I live and work in Germany. Now we're going to have a game. Sprechen Sie Deutsch? Sehr gut. Ein bisschen, okay. 3 years of my life I lived in France. Also, parlez-vous français? No one wants to confess. You all speak French if you speak Italian, but... Okay, and I'm Russian, so кто говорит по-русски? Здравствуйте. Okay, I will continue in English. I think it's better. By the way, who speaks English? Right, very good, very good. Okay, coming back to being two places at the same time. Be ready. I will tell you something very, very strange now. So strange, you will think it's crazy. It's unbelievable, bizarre, weird, really unusual. If this is what you think when I tell you, it's all right. It's all right because is this what physicists were thinking through the last 100 years? And in the beginning, and 1900, they were just terrified by what I'm going to tell you now. But they had a long work and a good time proving that it is true. So the bizarre thing is, quantum object can be in two places at the same time. Whoa. And, of course, it can move two paths at the same time. You would like to go to a cinema and you would like to go to your friend. You cannot. Quantum object can. Okay? So we remember this strange thing, and we're going to come back to it. But before that, I want to ask you, each of you, tell me one word which comes into your mind when you think about quantum physics. Have you heard about it? Something? Maybe in the movie? Or in the... We're gonna get the words now. Some word? You heard before? Yes. About quantum? What? I don't remember when. Approximately? Cinema. In the cinema. Something from the cinema. Okay, think. I come back to you.
Something with atoms.
Atoms. This is a really great word. Uncertainty. How beautiful it is.
Sheldon Cooper from...
Sheldon Cooper! Yeah, Sheldon Cooper.
The Bell experiment.
The Bell experiment. You know too much. Let's get out of... Let's rid of this guy. No.
Schrödinger?
Schrödinger. You love cats. You must be loving cats. I'm sorry.
Entanglement?
Entanglement. Oh my God. I'm not going to tell you anything new.
I don't know.
Lasers.
Lasers! Right. You got it. You remember?
The protons.
The protons. Oh, black. Sorry, I'm forbidden. I know. I cannot do that. Really nice. So, protons, atoms, uncertainty, Sheldon Cooper, Bell experiment, entanglement. You sit next to each other. You must know each other, no? Huh? You're talking about the same thing. What was that? Entanglement too. Schrödinger. Okay. Schrödinger, entanglement, and lasers. So we are all right. It's all about quantum. It's all about, you know a lot. I'm really happy. And, right. So let's except for 1 second that quantum object can be in 2 places. Okay? Just for a second. No worry. Now I ask you a question. Can it be in 3 places? Yes. Who thinks yes? Put up your hand. Okay, yes. Yes. Okay. So, 50%. Who thinks no? Never. Just 2. Enough. Come on. It's already bizarre. Okay? 2. Okay. So, we are very democratic. Everybody have their own opinion. The rest, I think, I don't know, right? It's the best. Uncertainty is the best. Okay, if it can 3, those who believe in 3, do you think 4 can also be? Why not? Okay, and then we can go for 5, 6, and so on and so on. And so now, be ready, there is coming a second very crazy thing. In fact, it's even worse. The quantum object is never in one localized place, is delocalized. It's like a little cloud. It's over an area, okay? I know it's strange. I'm sorry, but this is how it is. Okay, if it's a spread over, if it's this fuzzy, not sharp as we used to know, but fuzzy. But if it's fuzzy over an area, then we can think, okay, let's divide this area into pieces. 1 piece take here, 1 piece take there, 1 piece take there. So it becomes a little bit more easy to accept that it can be separated, no? So from one problem of crazy thing, we go into another problem of crazy thing just to play. And this is how physicists went from this through 100 years of developing quantum mechanics. It was not an easy way. Some of them suicide. It was really hard and difficult to believe. Okay. But how did it start? Why did they need to come with this crazy idea? Well, it all started with the strange behavior of an atom. An atom for physicists was really unclear object 100 years ago. Okay? Now we know everything, we think so. Much more than 100 years ago. But 100 years ago, it was like, what is inside of an atom? What is inside of an atom? Let's see what is inside of an atom. A nuclei is very small, and around the nuclei there is something which is usually called electron, okay? And depending on an atom, hydrogen has 1 electron, lithium should have 2, and so on, and 3, and so on along the Mendeleev table. So there are more and more and more electrons, and they are somehow around a nuclei, okay? They can be in different shape, can be very beautiful, not only sphere, very artistic atom, okay? And then they come more and more and more and more. Right. But why is this all everywhere? It's not here and it's rotating. No. Only the fact that it is everywhere at the same time helped us to understand the structure. Oh, this is too early. Stop. Too much. Okay, so there is this strange thing because in the atom we have electron somewhere and then nothing. Electron somewhere else and then nothing. Electron somewhere new and again nothing in between. Why nothing in between? Why cannot electron just go around the way it wants, come closer and farther and everything? It does not. Because if it does, it would follow a nuclei and there wouldn't be any atom. They wouldn't be you, they wouldn't be me, they wouldn't be a mini maker fair. A matter would not exist, but it exists. So, to make it possible in our theory, we have to screw up something else. We had to mess up with something we already knew. And what helped is to say, electron is not in one place. It must be everywhere around, then it cannot fall. Because things which are so strange, they don't behave the way we know. They behave strange. Okay, this is how physicists make new theories. New theories are always strange, because they shouldn't be like all theories. Okay, so, by the way, it was 50 years from the beginning of an idea about an atom until we understand, all right, this is how an atom looks. 50. It's not one day, it's not 2 days, it's not a week, it's not even a month. It's 50 years of work of tens of scientists. Okay, now we got an atom. Actually, an atom was this strange quantum object which scientists first managed to spread into 2 places. Okay? So atom was the first one. How do we hold an atom? An atom is 10 times smaller than a human. So we are about 2 meters, no? A bit smaller in my case. So 10 times smaller is 10 centimeters. 10 centimeters. 10 times smaller is 1 centimeter. 10 times smaller is 1 millimeter, and this was 4 times. 6 times more, smaller. This is how small an atom is. We cannot touch it. Our fingers are too fat, too big. We cannot touch an atom. To understand how big, now, take a person. Let's magnify ourselves 10 times, 10 by factor of 10. Okay, 1 meter, 10 times, 10 meters. 10 meters can be a small house, no? Times 10, 100 meters. It's already it's almost an Eiffel Tower, by the way. Eiffel Tower is 120 meters. Okay? So, it's 2 times. Third time, 1,000 meters. Jesus, this is a good mountain. We can already ski downhill, no? And this is 3 times. More, 10,000 meters. There is no mountain of that height. 9,000 something, no? It's just, more or less, just the last one. And this is 4 times. 10 times more, 100,000 meters. There is no object on Earth we know of that height. Okay? And this was 5 times. If we continue, we become so big that the sun is a little ball in our hand. Okay? This is how a size of an atom, if it is a human, is compared to size of us, if we are magnified 10 times. So it's a ball. The sun is a ball. And now I ask you, okay guys, now you are so big, you are so strong, find me this human on Earth. It's like, Earth? I barely see Earth. I only see sun. And you want me to see human? Come on. This is too much. I cannot do that. So, what can hold an atom? what can make things stop and move? Which kind of force can attract or push without touching? What can attract? Well, apart from beauty and all that stuff, something else, what can attract? What attracts things to Earth? What's that? Gravity, great. So gravity attracts things to Earth, also atoms to Earth, everything. It attracts everything. But to hold an atom between Earth and something else, right, we need a second Earth. So that it is in between. It's attracted to one Earth and to another Earth, and it's not moving. A little bit complicated, no? To make another Earth next to us. Okay, does not work. What other force do we know which attracts? Something about charges. No, do we know? If we electrify and then we put a paper, the hairs will stand up. No, we don't touch, but they stand up. Electricity, no? It's electric force. And electric force is all about light, in fact. Light is also electromagnetic field. It took us a while to understand that, okay? But when we understood an atom, after 50 years, we also understood that we can make a laser by using atoms. A laser, what is a laser? It's very bright here. I'm not sure we will see. And it's also not working. Okay. Do you see a green point on the wall? A green point on the wall? Do you see? Okay. So, it's from here and it's going to the wall and it's very small. So light goes all in one direction, right? How do we make light go all in one direction? Let's take a look. Let's take a look. This is our fellow friend atom, okay? And it can be normal, cool, in the ground state, or excited. Electron is farther away and it's really energetic, so two levels. Now this is light, comes into an atom and two quantas of light go away. Atom go down and it gives one quantum of light. So was one and appear two. Now we have a lot of atoms, a lot, and they are all excited. And light pass from 1, 2, from 2, 3, from 3, 4, and all atoms are coming down, one by one. And instead of hot atoms, we've got light. You make a hole and it goes out. This is how the thing works. Okay. How does it help us to make a quantum object move two paths at the same time? Now, our hands don't work to hold an atom. Gravity doesn't help to hold an atom. Lasers, on the other side, help. Because if you see that beam, right? Imagine you make many beams. It's like a wall, no? It does not, you can pass your hand through it, but it looks like a wall of light because it's all going in the same direction. So, in fact, this wall can stop an atom. Okay? An atom comes and reflects. It's very light. It does not go through this wall. If you put another laser on another side, then it does not go again. And so you can trap an atom in a light box. Okay? Bizarre, again very surprising, but this is why quantum physics is very exciting. Everything is strange, practically. Okay, so here is the message. We all know that lasers, they can heat, they can burn, they can cut, no? We use lasers to cut metal, to operate the eye, we can cut a little bit the eye and then repair it again. So lasers can heat, give energy to something. But not only. Lasers can also cool. Imagine this great thing. My nephew always wants that. You have your bottle of Fanta at a room temperature. Not nice, not nice. You take your laser, zip, and it's ice cold. Nice, no? It's like you don't need a fridge, you just need a laser, zip, and your it's cold. And I thought, this will never happen. And then I ask people who work on that, and they say, but this is how we cool satellites outside of Earth. Because if you send a fridge there, it will be too much. You need another way to cool a satellite. And it heats up because there is a lot of computers, there is a lot of machine inside. It needs to be cold. In fact, they use lasers to cool these things. It has to be a correct laser. Not all lasers will cool all objects. No. You have to arrange proper conditions, but it's possible. Okay, now, we take our atom, we take our laser, we cool it, we hold it. Now an atom has to be in the box. It cannot move. Okay, so in the box, atom has to behave according to rules. A little bit like electron inside of an atom. And so if it is in the minimum energy, really low, it has to be like a little cloud, just a little bit around the center of the box. Now it sits there in this little cloud, and that's it. Okay, now I say boring. I give you a kick. Now I go kick, and then an atom goes excited, and when it goes excited, it has to separate in two, because this is how the box rules work. If atom is in the box, in the excited state, it has to separate in two. But it's not really separation, right? It's still one atom. We don't create two atoms, it's still one atom, but it's delocalized around one side and around the other side of a box. You can think it's crazy and strange, or you can think, wow, it's excited and unusual. So both was happening, but the first experiment when we did this kind of thing happened in the 90s, only about 20 years ago, because we needed a really good lasers to make that thing work. So, now, if we can split it into two places, can we split it into three? Who agrees we can split it into three? Okay. Okay. How do we do it? To split in two, we need a kick. To split in three, einmal kick. No, one more kick, exactly. So you kick it again, and it has to go to another excited state. And so another excited state is exactly a little bit in the middle, a little bit on the side, and a little bit on the other side. Now we are masters. We can split our atom into as many locations as we want, just by keep kicking it. Okay? So that's how it works with an atom. Now the question is, if we accept that it is delocalized, do we think that if we ask it, please, 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 localize again, we take all the lasers away, you are alone, can you be again localized? Please? Will the atom localize? Do you think it will localize? You know the answer. Do you think it will localize? Do you think it will not localize? I see there is some. Okay, so in 1927, there was a young physicist whose name is Heisenberg, Werner Heisenberg. He was very young. All creators of quantum physics were young because you have to give freedom, you have to be free. And he came and said, you know what? This delocalization, like what is the space over which our atom is spread? We call it delta X. In fact, if you multiply it by, so P is the momentum, is how fast a thing moves. In fact, the momentum is also not clear. A little bit fast, a little bit slow, it's also uncertain, okay? So there is this uncertainty in momentum, and you multiply. And this thing is bigger or equal than a constant divided by 2. Okay, so we multiply two things. If this thing is 0, means that our atom can localize and can be a good atom the way we used to think about it. So this thing is 0. But if one of the two in the product is 0, it will be 0, right? If you multiply something with 0, you get 0, nothing else. But these genius physicists say, it's never 0. It's always more than a constant. And this constant is called a Planck constant. Planck is another genius physicist, but he was old when he discovered the Planck constant. And it's a very, very small, it's so small that we will never see it by our naked eye, how much the atoms is delocalized. So it's too small, but it's never 0. So even if we pray, our atom will not localize. That is the point. Right. You've done a great job. How much time do we have? A couple of minutes. Okay, now, a quantum object is delocalized. One thing. A quantum object can be split in two areas and move to pass at the same time. A second thing. Now I want you to make a little exercise. Turn on your fantasy. Choose one of the three objects. A bird, a boat, or a person, okay? I will give you a piece of paper and pencils. And I will suggest you to do the following. Separate the paper in two, okay? Separate the paper in two. On one side of the paper, make a little drawing, very simple drawing. One of the three objects in motion, a bird fly or a person go, something that we see every day around us, okay? So make it on the left side, and then be a child, please. Let your object be quantum and draw all what your fantasy let you draw, knowing of how quantum object can move. Okay? Let's try. I put on some music just for fun.
I love my God, God made me. I love my God, God made good. I love my God, God made good. I love my God, God made bad. I love my God, God made but I don't wanna pray to my maker. I just wanna be what I see, not just who I am, but the pink and golden land in that wide, wild sky over me.
Help me to the sun.
See, I'm looking everywhere. See, I'm looking to become not the prayer, but the prayer. And I don't wanna pray. I say I don't wanna pray. And I don't wanna pray. I don't wanna pray. I love my God, God maker. I love my God, God maker. I love my God, God maker. I love my God, God maker.
I ain't got it, Mama. What I'm saying isn't fair. See, I'm looking to become not the prayer, but the prayer.
And now
I don't wanna pray, no.
you say
I don't wanna pray, no.
oh, now
I don't wanna pray.
don't wanna pray.
I love my God, God made love. I love my God, God made good. I love my God.
God made good. I love my God, God made bad. I love my God, God made me.
Ricordiamo a tutti gli amici che stanno partecipando alla fiera che nella parte superiore c'è il Fab Lab e accadono delle cose molto belle. C'è la versione in 3D dei quadri di Aldo Famà, quindi un'esposizione unica, e poi c'è anche un'esposizione artistica di una macchina che misura il dolore personale e tante altre cose molto curiose su al Fab Lab.
God made good. I love my God, God made good. I love my God, God made good. I love my God, God made bad.
Okay, someone has finished? Yeah?
But I don't wanna pray.
Bring me some.
I just wanna be what I
Thank you. Oh my, wow, that's a very artistic one. I will try to guess and you correct me, okay? So there is a ship. There is a ship. Here, there is a bigger ship, which means spread in space, right? Okay. And then there are a lot of small ships, which inside of it. Very nice. Thank you very much. Hers is ready? Okay, come. Okay, here we have a bird which is flying down to catch a fish, I suppose, no? It looks like it's going so down. Okay, and then here we have extra two birds. Okay, and here we have a lot of fish, in fact. One fish delocalized. Huh? Okay, it's a tough job for a bird to catch a fish which is delocalized, because one time it will find it here, one time it will find it there. It does not know where it finds the fish, because this fish is spread over the whole area. This is a great drawing to explain how detection or observation works in quantum world. I didn't tell you about that, because I just said, it's spread over. But how does it look like to us? Will everybody see us in two places when we are delocalized? In fact, no. We are in two places, but if someone will look at us, he will always see us somewhere. But the point is that it could equally probably see us in one place and equal probably see us in another place too, which generally does not happen to localized objects. Right? Okay, this is great. I see a lot of birds there. They're very beautiful. Thank you. Okay, so there is a bird. It's flying, I suppose. It's flying. And then, oh my God. Oh my God. Delocalization is a terrifying process, I must admit, because it looks like a head of a bird flies up, the legs of the bird flies down, and the wings are also flying away. What can I say? This bird can catch a delocalized fish much better. Very, very nice. Thank you very much. Okay. I think with this fun, I thank you very much for being here and for doing great experiments, fantasy experiments in your world. If you can share with me your drawings, I promise I will not sell them for a lot of money. I will only keep them for my record of creativity. And I wish you a great day in this magnificent Mini Maker Fair. And say you goodbye.